So let's recall the example that we did before when we have the one-dimension domain. This is example. Mostly we are looking for the upwind scheme. So in the previous example, we had that linear domain. Phi A is equal 1, and phi B is equal 0. Rho is 1 kilogram per meter cube. And we had the kappa value. I'm just going to recall these values here. The kappa value is equal 0.1 kilogram per meter second. And we had the A is equal 1 meter square. These are the conditions. The total length of the domain is 1 meter. Then I'm going to pick the case when the velocity was actually 2.5 meter per second. And when we did this case using the central differencing scheme, we got divergence solution, right? And the only way to solve that problem was actually to calculate, because the Beckley number, cell Beckley number was actually 5. And you have to break down your cell. Instead of using 5 cells, we have to use 20 cells to be able to match the analytical solution, correct? In this case, I'm going to use 5 cells. This is the U. I'm going to use 5 cells in this problem, but instead of using the central differencing scheme, we're going to use the upwind scheme. And as we mentioned before, the upwind scheme has the provides one of the advantages is it can provide a stable solution for large cell Beckley number. So let's see if the upwind scheme would actually solve that problem just using the 5 cells and compare the solution, numerical solution, to the analytical solution to ensure this is true in this case. As usual, we're going to start with all the interior nodes. Which is 2, 3, and 4. And the general equation that we use is F east, phi east, minus F west, phi west is equal to kappa east, A east, d phi by dx in the east, minus kappa west, A west, d phi by dx on the west face. And there was no source term in this equation. We know that F is equal rho A times U, right? And we have D is equal kappa A over delta. And here we are picking delta X. Delta X east is the same as delta X west, right? There's no difference here. So D will be the same. So this will lead to D east is the same as D west, as the same as D. And we will have also F east is the same as F west, and nothing will be different here. Let's calculate the value of F. F is rho is 1, and A is 1, and U is 2.5. So the F value is 2.5. Then I have D, kappa is given by 0.1. The area is 1. And since we divided the 1 meter into 5 domains, so that distance is actually 0.2. So delta is going to be 0.2. So this would actually be 0.5. So D is 0.5. You call it D, you call it D east, you call it D west, is the same. And the F is equal 2.5. So if you want to calculate the Beckley number, cell Beckley, it is F over D. So it's going to be 2.5 over 0.5, and this is equal 5. So if I use the central differencing scheme, number 1 is not recommended for this case because it's always for Beckley number less than 2. But when we used it, we got the diverging solution, right? So now I'm going to use the upwind scheme here. So let's do, so I have F east. Now we are looking for the interior nodes. So this is one of the interior nodes, P, and this is E, and this is W, and this is the west face, and this is the east face. The flow is going into that direction. So if you want to get phi east, is going to be the upstream node, so it's going to be phi p. So phi east should be the phi p, and the phi west phase should be equal the phi of the west node. So phi west phase is equal phi of the west node. So if I substitute into this equation, I would have f east phi p minus f west phi w equal to, now for the diffusion term, d phi by dx, it's not going to change. It's going to be phi east minus phi p divided by delta x east, and d phi by dx, this is at the east face and this is at the west face. It's going to be phi p minus phi west divided by delta x west. So when I substitute here, I will end up having d east, phi east minus phi p minus d west, and this will give me phi p minus phi w. Let's collect the terms. So I have f east in the phi p. I would have d east, which is this term. I will have d west as well. This is totally in the phi p, and this should equal to, I will have d east phi east. I will have d west plus f west multiplied by phi west. So my a east, this is my a west, and here I will add and subtract f west. So I will end up having d east plus d west plus f west plus f east minus f west. This is multiplied by phi p equal d east phi east plus d west plus f west phi west. So this is again my a east, this is my a west, this is my minus sp, and this is my a east, and this is my a west, and the combination here give me the AP. So let's write down the coefficient here. So A east is equal D east, which is equal to numerically it's 0.5. A west is equal to D west plus F west, which is equal to D is 0.5 and the F is 2.5. So I'm getting 3. Now I will get SP is equal to minus F east minus F west. And for the mass conservation and steady state, this will be 0. Then I will have, we don't have a source term, so SU is going to be 0. And the last term is AP, which is equal A east plus A west. And this is already 0, so AP will be, as a number, will be 0.5. Let's add them. So it's going to be D east plus D west plus F west, which simply 2D plus F, right? Because D east and D west are the same. So numerical will be 2 times 0.5 plus 2.5. So that's going to give me 1. That will give me total 3.5. So these are the coefficients for the interior nodes, right? That's for node 2, 3, and 4. So this equation is simply AP phi P equal A east A east phi east plus A west phi west, and I know the value of each one of these coefficients from here. So these are the interior nodes. Going for node number 5, the one to the right. Let's actually draw the domain again. So this is phi b equal 0. And this is node 5, which I'm going to call it P. And this is node 4, which is the west. And there's nothing in the east here, right? So that's just this. That's number 2. It's node 5. Again, the equation is F east phi east minus F west phi west equal kappa east A east d phi by dx on the east face minus kappa west A west d phi by dx on the west face. Where are the east and west face? This is the west face, right? And the east face is overlapping here. So that's my east face, right? And the flow direction is in this way. So if you want to get, this is phi east, and this is phi p, and this is the flow direction, and this is the flow direction here. So this is phi west, this is small w, and this is the capital W. So let's do the approximation here. So what is phi east? According to the upwind scheme, phi east should equal to the phi of the upstream node, so it's going to be phi p. What is phi W? The west face phi, according to the upwind scheme, should be the phi of the node W. D phi by dx on the east face. Now, this will be the linear change, right? So I'm going to calculate that based on delta x node. So it will be phi p, phi b, divided by, this is phi p, and this is phi w. So for the east face, I will have phi b minus phi p divided by delta x node, which is delta x node is half delta xe, right? And d phi by dx on the west. This is what we used to do in the diffusion problem, right? Just to recall that, or go back and watch the videos. You'll figure out what we do for the diffusion when the node is close to the boundary condition or the boundary phase. D phi by dx on the west will be simply phi p minus phi w divided by delta x west. I know that delta x node is half of delta x east, or it is half delta x west. We know that. And we know that if east equal if west equal f equal 2.5. We know that d east equal d west equal d, which has a value of 0.5. So let's substitute into this equation. I don't think so we need this anymore. So f east times phi east will be phi p minus f west times phi w, that's w small, will be phi w capital, equal to kappa east A east over delta x node multiplied by phi b minus phi p minus kappa west A west over delta x west multiplied by phi p minus phi w. And there's no source term here. So let's collect the term. What we have, I will have 0 phi east. There's no east node actually to consider. Now I will have, this is d, right? This is, that term here is d west, call it that d west. This is not d east. I know numerically it is double the d east or 2d, but I cannot call it d east, so keep it that way. So what do we have? I will have plus, I will have d west, phi west, and I will have kappa east, A east over delta x node, phi b. So I took that term, and I took that term as well. So the two remaining terms are phi p. Oh no, actually we have f west here, so that's plus f west as well. This will come to the other side, right? So the left-hand side will be simply the phi p thing. So I will have f east, I will have kappa east, A east over delta x node. I will have d west. This is multiplied by phi p. Let's double check that here. So I have f e phi p. I have, this is negative, will be positive, kappa east, A east over delta x node phi p. And I have a third term that's going to be positive, which is d west phi p. So that's my A east equals 0. That's my A west. This is my SU term. Here, I'm going to add F west and subtract F west. So I can take that term and call that A west, right? So I have if I have Kappa east, A east over delta X node, I have D west plus F west. I have F east minus F west, right? This is totally multiplied by phi P. So I can call this A west, this term and this term together are minus SP. Okay, then the total combination here is my AP. So if I write down this equation in a more organized way, I would have A west plus F east minus F west plus Kappa east, A east over delta X node. This is totally multiplied by AP equal, phi P, right? And that's equal to 0 phi east plus A west phi west plus SU. Now let's write down the coefficient here. Again, this will be AP equal AP phi P equal 0 phi east plus A west phi west, but I would have SU term here. This is a general equation for node number 5. Let's write down the coefficient here. What is A east? It is 0. What is A west? A west is D west plus F west, which is simply D plus F. D has a value of 0.5 and F has a value of 2.5. So this will be 3. So for that point is A west is equal 3. Now SU. SU is equal Kappa east, A east over delta X east phi B. And I know that phi B is equal to 0. So SU will be 0. Then let's look to the SP. What's my SP? SP is equal to, this is totally the SP term. It's going to be minus F east minus F west plus Kappa east, A east over delta X node. I know F east and F west are equal. So I will have minus Kappa east, A east over delta X node. Delta X node is half delta X. So this will be simply 2D minus 2D. How much the D value is? D value is 0.5, so that's going to be minus 1. Now AP is simply you add up A west, right, which is D plus F, plus this is 0, that's canceled out, and this is 2D. So I would have A west, which is D plus F, so I would have 3D plus F. So this will be simply D is 0.5, so that's going to be 1.5 plus 2.5, I will get 4. That's the node number 5. We still have one last node to finish, which is node number 1. So let's draw the domain. This is node 1. I'm going to call that P. This is actually node 2. I'm going to call that the east. Now, this is the east face, and the west face will be overlapping here. That's the west face. I know the value of that boundary is phi A equal 1. The flow direction is in this way. So we have the same. I'm going to call that distance here is delta X node, right? Delta X node is half delta X, east or west, either one. Again, we have F east equal F west equal F. Value or numerically, it's 2.5. I have D east equal D west equal D, and that's 0.5. We have phi A is equal 1. So the governing equation for node number 1, node 1, F east phi east minus F west phi west equal kappa east A east over d phi by dx on the east face minus kappa west A west d phi by dx on the west face. Okay, we are using the upwind differencing scheme, right? So the flow is coming this way. If this is my phi east, so this is a flow, right? That's phi p. So phi east is simply equal phi p. What is phi on the west face? It is phi a. It's already given. So I don't need that value here. Then let's do the gradient. D phi by dx on the east face will be simply phi e minus phi p divided by delta x east. When I go to the west face, d phi by dx on the west face will be phi p minus phi west, which is phi a, right? It's phi a divided by delta x naught. These are the approximation here. Let's actually substitute into the big equation. So I have F east, phi east is going to be phi p minus F west, and phi west would be phi a equal to, I will have kappa east, A east over delta x east multiplied by phi E capital minus phi P. Then I have minus kappa west, A west, this time is divided by delta x naught multiplied by phi P minus phi A. Let's distribute the terms here. What we're going to have, I will have kappa east, A east, delta x east, that's actually D east. That's D east times phi east. So I finished that term. What else we have? That's P, that these two terms will wait a little bit. I will have kappa west, A west over delta x naught, that's time phi A. Then I have F west, also times phi A. So I'm going to collect the terms here, and this will be the term here. Okay, then what else we will have? I will have 0 phi west. I have nothing in the west. There's no cell in the west side. Now let's look to the phi p. I have F east times phi p. I have kappa east, A east, delta x east. This is actually D east, right? So D east phi p. So that's plus D east. And I have plus kappa west, A west divided by delta x node times phi p. 3 terms here. Okay, now this is A east. A west is 0. That's totally my SU term. So I have A east is already here. Then these 2 terms together will be actually the minus SP. So I can write this equation as, again, and the combined terms here, that's my AP. So the equation can be written as AP phi P equal A east phi east plus 0 phi west plus SU. Now, what are the coefficient values? A east is equal D east, which is equal D, which is equal 0.5. A west is 0. Let's get the SU. SU is equal to this term here. This is kappa west, A west over delta x naught, and delta x naught is half delta x. So this will be simply 2D plus F west is the same as F. So I'm going to put F in here. 2 times D, D is 0.5. That's going to give me 1 plus 2.5. This will give me 3.5. Then let's do the SP. SP is equal to minus FE plus kappa west, A west over delta x naught, which can be written as minus F plus 2D, which is minus F is 2.5, 2 times D, that's going to be 1. It's minus 3.5. What's left is AP. AP is equal to A East plus F East plus Kappa West, A West divided by delta X node. This term here is give me minus, that's going to give me F plus 2D. And this is D plus F plus 2D. I got 3D plus F. So 3 times 0.5, that's 1.5 plus 2.5. That's going to give me 4. So now I collected the coefficient for this one here. So the next step is to actually build the coefficient table. This is very important. So let's collect the pieces in one table. So that's node 1, which we just finished right now. So I'm going to build my table. I'm going to have the table of coefficient. That's node 1, node 2, 3, 4, and last is node 5. And I'm going to put that A West, A East. I'm going to put that SP. I'm going to put that AP. I'm going to put that SU. And we have the symbolic and numeric values for each one of them. So node number 1, A West is 0. I'm collecting from what we already just did right now. So A West is 0, A East is D, SP is minus F plus 2D, minus F plus 2D. That's SP. AP is 3D plus F. And SU is F plus 2D, 2D plus F. Yep. And going for node number 2, this is an interior node. We got A East is 0. We got A West is D plus F. And we got SP is minus 2D. Let me review that interior node. Okay, just a second here. We are in A West is F plus W. A East actually is DE, sorry. D. Then SP is minus, it's actually 0. SP is 0. And SU is 0. And AP is 2D plus F. And we're going to repeat that for the coming 2 lines here. Let's just put the values here. F is equal to 2.5 and D is equal to 0.5. Then for node number 5, we got A East is 0. We got A West is F plus D. We got SP is minus 2D. We got AP is 3D plus F. And we got SU is equal 0. Now, numerically, for node number 5, we got A West is 3, 0, minus 1, 4, and 0. For the interior nodes, let's look at the values. A East is 0.5, 0.5, 0.5. D plus F, which is the West coefficient, that's 3, 3, 3, and 0 is here. 2D plus F, that's the AP. AP is 3.5, 3.5, 3.5. And that's it. We got all the number. No, node number 1. I missed this one. That's 0. That's just put zeros here. So we have the red color writing. D is 0.5. SP is minus F plus 2D. It's minus 3.5. And AP is 3D plus F, which is 4. And SU is coming to be 3.5. So this is simply the table of coefficient. Let's build the matrix. Okay, let's build the matrix. Coefficient matrix. Okay, so we have, let's actually do the, let me use a lighter color a little bit, so we can actually, so I have 1, 2, 3, 4, 5. I have 1, 2, 3, 4, and 5. Okay. Here I'm going to have phi 1, phi 2, phi 3, phi 4, and phi 5. And here I'm going to have the SU coefficient. So I'm going to have 3.5, have 0, 0, 0, and 0. Now let's put the coefficient here. Diagonal is the AP coefficient. So this will be 4. This will be 3.5. The next one will be 3.5. Next one will be 3.5. Next one will be 4. Okay, now go for node number 1. What's the east side coefficient? It's 0.5. Go for node number 2. I have east and west. A east is 0.5. Remember, we're going to put negative for the east and west coefficient. Then we have the west is 3, so that's going to be -3. Then you repeat the same for the interior nodes. Now going to node number 5. I don't have anything in the east, but I have a west coefficient, which is -3. Then you fill the empty spots with zeros. Then you can solve that matrix using the MATLAB and get the values. I got the values. Phi 1 is equal 0.9998. I got phi 2 is equal 0.9987. I got phi 3 is equal to 0.9921. I got phi 4 equal 0.9524. And lastly, that phi 5 is equal to 0.7143. So these are the values numerically we got when we use the upwind differencing scheme. If you recall, when we use for the same part, the same example here, when we use the central differencing scheme, what were the values? We got this value is 1.0356. This one was actually 0.8694. This one was actually 1.2573. This value was actually 0.3521. And the last one was actually 0.4644. So this was the central differencing scheme. This is the upwind differencing scheme. So we got unstable solution when we used the central differencing scheme because of the Searle-Bickley number was 5, which is breaking the stability condition of less than 2. But when we use the upwind scheme, we are getting reasonable results here. It's no longer diversion, it's actually a conversion solution. So I will show you a plot comparing all the cases that we did before in the previous examples. We did solve examples using the central differencing at lower velocity. Then we used the central using higher velocity, which is 2.5. So let me grab that part. So here's the chart I'm talking about here. So this is what we covered in the first example. This is the domain at lower velocity, analytical solution, and the central differencing scheme solution. We were able to get this very accurate numerical solution, right? When we went for the 2.5, this is for 2.5 meter per second. This is the exact solution, the analytical solution. We got that diverging one. For this case, Bickley was less than 2. For this one, Bickley was actually greater than 2. It was 5. That's why the central differencing scheme didn't work fine here, okay? Now, I did solve the two parts, the 0.1 and the 2.5. We did that together right now using the upwind differencing scheme. I did that myself. So you see that for the upwind differencing scheme at the lower speed, you are getting very accurate solution, very similar to what we did with central. So both of them works fine at the lower speed. But this is what happened. At high speed, Bickley number was 5, you got unstable solution. When you go for the upwind scheme, this is the results I just show up here. These are the values here, and you can see that we are getting closer using 5 cells. This is 5 cells. This is also 5 cells. We overcome this one when we did the 20 cells, which is a very long solution. But now I can still use a small number of cells using the upwind differencing scheme, and I can get good results. You see that there is some differencing here when the solution actually changed direction. You see that there is a little bit of separation, and this is something that we need to do work to improve the upwind differencing scheme. So now we solve from a diversion into a convergent solution by switching from central differencing scheme to the upwind differencing scheme. But I still see some error increasing when the solution changed direction, and this is something that we need to solve or improve the upwind. So we will take from the upwind, improve it a little bit, so we can actually eliminate that kind of error here. And this is what we're going to discuss in the upcoming report. One quick observation for this example before we leave that recording here. We constructed the matrix of coefficient here. So let's copy it and make some observation here. So we have the 4, minus 0.5, 0, 0, and 0. And we have minus 3, 3.5, minus 0.5, 0, 0. I have minus 3, 3.5. No, that's 0 first. Minus 3, 3.5, minus 0.5, 0. I have 0, 0, minus 3, 3.5, minus 0.5. I have 0, 0, 0, minus 3, and 4. So this is the coefficient matrix. We can quickly apply the Scarborough criteria here, right? Again, remember, this is your AP, right? So Scarborough criteria state that summation of the absolute value of the neighbor coefficient divided by the absolute value of AP should be less than or equal 1, with one node at least should be equal should be less than 1. So this is my AP, right? This is my AP. This is the neighbor coefficient, east. There is nothing in the west. So you take an absolute value here, so it's going to be 0.5 divided by 4. So the Scarborough criteria for the first line is going to be 0.5 divided by 4, which is less than 1. When I do the second line, absolute value of minus 0.5, that's going to half. Minus 3 is going to be 3 as an absolute value. So I have 3.5. AP 3.5, so I will have 3.5 divided by 3.5. So I have the equality 1. Then I have Scarborough criteria is going to be repeated for the 3 here. So it's going to be 3.5 over 3.5. I'm going to be 1. Also, I'm going to be 1. Here, I will have 3 over 4. So it's going to be 0.75. So number 1, all of them is less than or equal 1. And I have actually 2 nodes with inequality terms. So Scarborough criteria can be quickly checked from that coefficient matrix while you go. So you can do that quick check and write the value of that Scarborough criteria next to it. Number 2 is we didn't actually write down the equations for the nodes, right? So for the node number 1, we end up having this is the equation here, right? So I can actually, let's actually overlap. So what I have, this is for node number 1. So AP is node number 1. So I have AP, which is, as a value is 4, phi 1 equal to phi east. Remember, the nodes are here. So that's phi A, that's phi B. And this is 1, 2, 3, 4, 5 cells. Node 1, node 2, node 3, node 4, node 5. So I'm writing the equation for node number 1. So this is the general equation here. That's node 1. That's what we derive. We derived for node number 1, AP phi P. AP has a value of 4 times phi p, I'm looking for node number 1. Phi east is 0.5. And the east node, phi east is phi 2 plus 0, that's gone, and SU is 3.5. Now let's go for node number 2. I will find the interior nodes relationship. This is the relationship that we got for node number 2. It's AP phi P equal A east phi east plus A west phi west. AP is 3.5, so I have 3.5. Now I'm at node 2, that's phi 2, equal to A east is 0.5, times phi east, which is phi 3, plus A west is 3, and phi west is phi 1. Do the same for node number 3. You will have 3.5 phi 3 equal 0.5 of phi 4 plus 3 of phi 2. And for node number 4, you will have 3.5 phi 4 equal 0.5 phi 5 plus 3 phi 3. Now we need to go for the node number 5. I have the formula for node number 5, which is right here. AP phi P equals 0 phi east plus A west phi west plus SU. AP is calculated up here, it's 4, so that's for node 5. I will have AP, which is 4 phi 5 equal to 0 phi east, so I don't have anything in the east. AW, which is 3, and the west node is phi 4 plus SU, which is 0, simply. Nothing. So that's the equation, nothing else. Okay, so, and if you rearrange the equation here, you will get 4 phi 1 minus 0.5 phi 2 equal 3.5. You will get 3.5 phi 2 minus 0.5 phi 3 minus 3 phi 1 equal 0. 3.5 phi 3 minus 0.5 phi 4 minus 3 phi 2 equals 0. I have 3.5 phi 4 minus 0.5 phi 5 minus 3 phi 3 equals 0. And the last equation is 4 phi 5 minus 3 phi 4 equals 0. If you look to these equations and you compare that to the coefficient matrix that we built directly from the coefficient table, you should get the same. So I have 4 phi 1 minus 0.5 phi 2 equals 3.3. Then I have minus 3 phi 1 minus 3 phi 1, 3.5 phi 2, and minus 0.5 phi 3 equal to 0. And the rest of the equation is satisfied here. I'm just double checking if you build up these equations manually and you try to extract the coefficient matrix, it's exactly matching correctly what you build using the coefficient table here. That's why it is very important to write that coefficient table to be sure that everything is done correctly. That's it for this example. Again, we would like to improve the error when the solution is changing direction here for the upwind differencing scheme. So we need to improve this one so we can actually minimize the error here, and that's going to be our next work.